co-chair of the conference. Reminding that Sebastian's presentation was the first among our best paper nominees, and now we will have two other presentations in the row for those which you can vote in the closing session. So keep your eyes and ears open. And the next presentation is going to be algorithmic planning, simulation, and validation of smart shared parking services using edge hardware by Murali Raman. He completed his master's in information technology at the University of Stuttgart and then joined Artemis as a working student, continuing to contribute to the projects in the company. And as a part of his thesis work, he worked on the concept called smart shared private parking using the Eclipse ecosystem. Currently, he is working as a software developer at Artemis. So, Murali, here you are.
Hello all. Just a minute, I'm sharing my screen. You all see my screen? Just a minute. Can you see now?
Yes.
Okay. Hello all. I'm going to present the results of my thesis and how we realize the concept of smart shared private parking using the Eclipse ecosystem. First of all, to introduce, the idea started with the concept of smart gate device. The smart gate device is conceptually in proposal by Artemis, and it's a kind of electrical garage device which is capable of sensing, actuating. And so we thought of employing this smart gate electrical garage device for the concept of smart parking. And for this smart gate to act as an interface, we thought of employing V2X communication. And in this research work, the contribution started with setting up the simulation-based testbed in which there would be a scenario input for which the system could react and produce results, which could be further processed for different outcomes. And particularly, the design of the system could be changed by employing some mathematical models and infer the outputs due to the changes in the system design. So the main motivation behind the work is the parking assault in the recent times due to the development of automobile, due to the development of automobile and mobility in real world. From a personal experience of mine, I found a friend who was parking 2 streets away, and he was always feeling insecure about the security of his vehicle. And so we thought of addressing the problem of parking through a shared parking model. There are shared parking model commercial providers, like example MobiPark, but we thought of doing a scientific work with the aid of communication that will rightly help to assess the effectiveness of such a model and help us to extend the idea to larger scenarios. Hence, we have the model of smart shared parking model to analyze in this work. So to start with, the system design and architecture. So the keynote speech by Robert gave a nice introduction to Sumo and its role in modeling mobility model and doing some analysis. And as rightly said by Robert, it could lead to innovations to a first step towards mobility innovation. And V2X frameworks could also be part of this mobility models and simulation. And we used Eclipse Mosaic, which is a V2X framework combined with a suite of simulators like communication simulator, network simulator, uh, traffic simulator, which is of course Eclipse Sumo. And for this research, we have started with extracting the data using OpenStreetMap, and the testbed for this research is based on the inner city of Dublin. And to start, we started with extracting the OpenStreetMap data, and then we conceptually deployed roadside units, which is conceptual deployment of the smart gate hardware. And these smart gate hardwares are deployed in various parts of the network, and they are deployed using geographic coordinates. And the vehicles flow through this entire network, and this helps to further analyze the parking model we have in place in the network. So the City of Dublin administration provides the data points, the open data for us to analyze the research, to go through the research. So this map indicates the recordings of inward and outward vehicles into the inner city of Dublin. And we have considered the entry point 31 through which the vehicles move inwards and outwards of the city. And based on this, we allowed the vehicles to go into the city and look for parking. And based on this, we go through the further research. So the system design started with coming up with a mathematical model. So the mathematical model in place, like the first mathematical model focuses on the preferred walking distance. So the vehicle owner could focus to park his vehicle or her vehicle in a certain location and could prefer to walk for certain distance. But at the cost of walking distance, he could also ensure the safety of the vehicle, provided the parking lot owner gives it. So the variable XMN is the decision variable that makes sure of various attributes like distance, the parking criterion given by the vehicle owners and the drivers, and availability of free spots, and also an allocation criteria which ensures that a vehicle is not allocated to the frequently used parking lot. And then comes the mathematical model 2, which ensures that which focuses on the overtime parking decision of a particular driver. So this is the architecture of the system, where this is for a particular parking request, and the parking request flows from the vehicle to the roadside unit, which again flows through a cloud-based web service in which there are different modules that takes care of different decision attributes. Say like distance manipulation takes care of matching a parking lot within the preferred walking distance of the driver. So this is like a miniature flow diagram that explains how a parking request and resume goes through the system. So the car driver, when he requests for a parking, then the request flows through roadside unit to the web service where the shared parking model is hosted, and the driver is given the response of parking lots, which is a geographic coordinate response through the roadside unit. And once the vehicle is parked, uh, the roadside unit informs the web service, and this is to ensure that uh, to track the parking request being served rightly. And then similarly, the resume request is used to estimate the overtime parking behavior of the drivers. So the parameters that are used to analyze the work in this research are vehicular emission, reroutes, and distance travel. So, and then utilization rate of the parking lots, revenue generated, and a correlation heat map to correlate different attributes and to arrive at a conclusion. So in particular, reroutes is a parameter which is particular to uh, Eclipse Sumo that estimates whether the vehicles are rerouted to another parking lot when the parking lot in consideration is full. So this is the simulation testbed we have come up with to analyze the shared parking model. So the V2X framework V2X framework, that is Eclipse Mosaic, takes care of deploying the different components like vehicular RSC vehicles and roadside units, and web service hosts the actual shared private parking model. And at the end of each simulation, we get the vehicular emission log from the V2X framework, and the web service gives the database records, which gives the utilization rate and revenue logs, which further helps us to process and consolidate data. And overall, the consolidation will give the results of the comparison analysis and correlation analysis, which help us to draw useful conclusions. First of all, we thought of generalizing a communication strategy because due to the development of 5G, mm, the communication technology of VANET might go obsolete, or it could change anyways. So even though we used VANET to analyze the communication strategy, here it is generalized. So with the employment of such a communication strategy, the vehicular emission is reduced because the commute time for a vehicle to search for a parking spot is reduced considerably. I'm sorry. Then of course the reroutes are also reduced because the vehicle driver is informed about the availability of a free parking spot in advance. And this is a much bigger scenario analyzed, and here we have compared the different hourly scenarios and with the availability of number of shared private parking lots. The first set of graphs tells us the difference between the vehicular emission difference between the model without the shared private parking model and the model with shared private parking model. As we can see, with the employment of more shared private parking model, the vehicular emission is reduced, and you could see in the tabular column that with the increase in number of shared private parking lots, the rate of decrease in the vehicular emission increases. Like the vehicular emission in this case is reduced to 7% with the employment of 4 more shared private parking lots. So in terms of utilization rate, you could see that in the base model without any shared private parking model in place, a particular parking lot is utilized more, and commercial parking lot is utilized more, and this will like make it like this is due to a strategic position of that particular parking lot. And with the employment of the shared private parking lots, the utilization rate increases and it considerably decreases the utilization of the other commercial parking lots. I'm sorry. And as revenue is directly proportional to utilization rate, the revenue of the shared private parking lots as a whole increases with its increase in the number of shared private parking lots. And finally, the correlation heat map. The correlation heat map gives an idea how the different parameters like vehicular emission reacts to the change in number of shared private parking lots. As you could see with the vehicular emission, and the parameter to consider is here is the ratio. The ratio denotes the number of shared private parking lots employed, and its relation with the vehicular emission is that just a minute, sorry. With the increase in ratio, the vehicular emission decreases by 30%, and with the increase in number of shared private parking lots, the number of vehicles that are served by the shared private parking model increases. And also there is another parameter to consider, which is the number of vehicles moving out of the model itself. So it decreases by 50%. And finally, this research proves the effectiveness of shared private parking model. So, and it is an improvement to the traditional model by lesser emissions. We have a comparison analysis to prove the effectiveness of the model, and also correlation analysis that helps to conclude the reaction of vehicles in model. And finally, we could, from the previous presentations, we could extend this as like a hardware in loop simulation using Eclipse Cuxa or some other right software stack. That's it from my side.
Thank you so much for interesting presentation. We have time for maybe two questions. So
I have a question. I would like to put in perspective with what we saw on sumo and also electrical cars. Now we see more and more location and electrical cars in city. Do you think that it could also help having this kind of tools available for managing parking lots, and where we could maybe have a first place where we could put the car and then after that use a rental car or to move inside the city? Did you have something in mind like that in your studies?
We haven't considered that, but it's an interesting point. But yeah, like also we have another thought that we also thought of employing bike as an intermodal travel option instead of the preferred walking distance, so that the vehicles could be parked in a distant location from the actual destination. And so this could offer further improvements in traffic scenarios, like reducing the traffic congestion in the actual destination. The point of the old research is to reduce traffic congestion, considering the vehicle owner and the parking lot owner's preferences. Yeah.
Yeah.
Thank you very much, Murray.
All right, our time is up. There was also another question which I forwarded from the audience. So you can maybe, Murali, look at that during the next presentation and give some answer.
Yeah, sure. Yeah.
That